All right, let's dive in. Today, we're talking about the hidden engine that makes modern AI agents, well, agents. We're going to forget all about those rigid if-then scripts because we're exploring how AI really thinks, how it decides, and how it acts in a world that is, let's be honest, fundamentally random. This is the stochastic compass.
Okay, put yourself in the machine's shoes for a second. You see two paths. Path alpha, 78% chance it's clear. Path beta, it's faster, but there's only a 45% chance of a clear run. What's the call? See, there's no single right answer because the future isn't a straight line. It's a massive, tangled web of probabilities.
And that right there, that's the core dilemma for any AI agent that has to operate in the real world. I mean, when you literally can't predict a single certain future, how in the world do you make a logical, optimal choice? How do you chart a course through what seems like pure chaos?
The breakthrough here isn't about writing a more complicated set of rules. No way. The real genius is giving the agent an internal compass, a mathematical tool that lets it listen to all that environmental noise and somehow, almost magically, turn that chaos into a clear, actionable signal.
So how does this compass actually work? Well, at its heart, it's a powerful mathematical idea known as a stochastic process.
Now, I know that sounds super academic, but the core idea is actually pretty simple. The stochastic process is basically a mathematical map of uncertainty. It's how an agent builds a model of a world where every single step and every piece of information has some element of randomness baked right in.
A really great way to visualize this is with the classic drunkard's walk. Just imagine someone taking completely random, unplanned steps. It seems aimless, right? But over time, they start to explore the space around them. And that's exactly how an AI agent starts to understand its environment, by exploring this huge landscape of possibilities, one random seeming step at a time.
This leads us to a really crucial concept called the Markov property. And honestly, it's a rule of radical efficiency. Just like the slide says, an agent's next best move only depends on its current position. It doesn't need to remember every single mistake it made along the way. Think about that. This frees the agent from what would otherwise be an impossible computational burden. So, how does the agent use this property to pick the best path forward? It uses a pretty cool technique called Markov Chain Monte Carlo, or MCMC. What it does, essentially, is hallucinate thousands upon thousands of possible futures, all starting from where it is right now. It runs all these tiny simulations, and then it simply picks the path that on average leads to the highest probable reward.
Okay, so the agent can map out the future. But here's the thing, not all randomness is the same. So in this next section, let's look at the different ways these agents actually read the noise.
We can pretty much group this into two big categories. First, you've got the Poisson agent. This guy is built for sudden, bursty events. Think of a flood of customer support tickets all coming in at once. Then you have the Gaussian agent. This one excels at smooth, continuous data, like the kind a self-driving car uses to navigate, filling in the gaps between sensor readings to create a seamless path.
So, what is the end goal of all these calculations? What's it all for? The agent is trying to find what's called its stationary distribution. You can think of it as achieving a state of equilibrium. It's that sweet spot where the agent has mapped all the probabilities so well that its long-term strategy becomes totally stable and optimized. It has, in a very real sense, solved its environment.
Now, I know this all sounds very theoretical, but this is the actual engine behind some of the most powerful AI applications we use today. So let's take a look at a few examples of these agents out there in the wild.
Let's start with high-frequency trading. The agents running these systems are not just following some simple buy low, sell high rule. They are navigating what's known as Brownian motion, the totally random, chaotic fluctuations of the market. They're executing trades based on the most likely probabilistic path the market is going to take in the next millisecond. It's incredible.
This kind of thinking is also completely revolutionizing large language models. Using these MCMC-based methods, developers can actually fine-tune an AI's responses on the fly. As the model is generating text, this stochastic process is working in the background as a real-time alignment tool, steering the output away from mistakes and towards more accurate, helpful answers. It's literally a compass for conversation. So what's the big takeaway here? After all of this, what is the true power that this stochastic compass actually gives to an AI agent?
It's this. An agent's real strength isn't being able to predict one exact future. I mean, that's impossible. Its real strength is its ability to calculate and understand the entire architecture of possible futures. It doesn't just see one path, it sees the whole map, with every single branching road and the probability attached to it.
So, to sum it all up, let's hit the key points. First, AI agents are navigators of uncertainty. They're not just following a fixed script. Second, their compass is the mathematics of stochastic processes, which lets them find that signal hidden deep inside the noise. And finally, their real power comes from mapping all possible futures, not just predicting one.
Because when you really think about it, in a world that is so fundamentally uncertain and chaotic, having a precise understanding of that randomness, well, that's the most rational and powerful tool you could ever possibly have.
So, where do we go from here? We want to know what you'd like to see next. Should we dive deep into hidden Markov models, the secret sauce behind modern speech recognition? Or should we tackle the absolutely massive world of reinforcement learning? Let us know what you think. Thanks for tuning in.